no secrets here.
Yeah.
These are two solutions of bicarbonate of soda, which is baking soda. Yeah, baking soda. Now, the one, we've taken the same amount roughly, and we've dissolved the one amount in a fairly large amount of water, and we've put in very much less water in the other. So in other words, the concentrations of those two solutions differ. This is a higher concentration than this one. Now, we have here some ordinary
vinegar,
catering sachets of vinegar. I'm going to put a certain amount of my vinegar in here. And of course, vinegar is an acid and it will react with the bicarbonate radical. And Tanika is going to put his in there. So, and we're going to put them in together, and we're just going to squeeze the amount in. Could you see what happened there? That has completely reacted, whereas this is still reacting slowly.
Quite slowly.
There you go.
Let me try and swirl mine. Maybe it can be faster.
It really doesn't make much difference, but this is making a very fruit salty kind of sound as we swill it around, because the higher concentration means that for the same amount of vinegar, we're getting far more successful collisions and hence reactions in this container as opposed to that one.
And the next one related to concentration, of course, is pressure, but that's when we talk of gases.
And then this temperature one, which is interesting.
Temperature, and when we started, that's the first one we started with, and we said it is related to the kinetic energy possessed by the molecules. Okay. So the higher the kinetic energy of the molecules, the faster they move around, and therefore the higher the chances of them colliding with other molecules for a successful reaction.
Let's just draw you a picture here. When you have a container full of molecules, those molecules are moving around, and you know about the kinetic theory that we dealt with in grade 11. Now, they're moving around, but they're not all moving at exactly the same speed. In other words, they don't all have the same kinetic energy.
Yeah.
Some will be moving slower, some will be moving very fast, but on average, most of them will be moving at some kind of speed that is related to the temperature, or rather the other way around. The average kinetic energy tells us what the temperature is. But if we had to draw a graph in which we plotted the number of particles moving at particular speeds, in other words, the number of particles with certain kinetic energies, this is the kind of picture that we would get. You see, a low point here tells us very few particles have such a low energy. On the other hand, on the other side, very small number of particles have a very, very high energy. And you can see that most of the particles have an energy related to what we call the average kinetic energy. So the average kinetic energy, the sort of mean energy, sits down the bottom and down the middle here. Some with fewer or less kinetic energy, some with more. But on average, that is what the average kinetic energy is. And if we were to measure the temperature, we would say the temperature is a function of this average kinetic energy. So if I double that, I double the temperature. Now, in the case of a reaction, we might say, well, the only successful collisions to occur will be amongst those molecules with a kinetic energy so much or more. Now, if we had to raise the overall temperature of this whole array of molecules, what would happen, of course, is that this average would move to the right. And in other words, more and more molecules would fall into this area here, which tells us how many molecules have the right average kinetic energy or kinetic energy. So the higher the temperature, the more molecules have sufficient kinetic energy to undergo a reaction and therefore temperature becomes a factor in increasing the rate of reaction.
Now, from the previous chemical reaction that we showed you, that's the reaction between vinegar and bicarbonate of soda, there are two ways in which we can measure the rate at which this reaction is taking place. One, we can be collecting the gas that is evolving from the chemical reaction and measuring the time in which the gas is collected, and we are able to find out how much of the gas molecules are collected per certain period of time.
And in a way, you would say that that is a measure of the rate.
That will be a measure of
so
the
it would
rate.
be something like cubic centimeters per second.
Exactly. Yes. So we
okay.
work from there. Or the second way of measuring it will be to have this chemical reaction all occurring placed on a particular scale that measures the mass of this substance.
As the gas
now,
bubbles
as the
off.
gas is evolving, bubbles off, get out of this reaction, what do we expect the mass to be doing here? Surely it will be decreasing, because we're taking, or part of this mixture is going out. So the rate at which the mass is decreasing per time will be telling us how fast the reaction is taking place.
Okay. Yeah. And of course, we always have to choose some measurable parameter in the reaction. So if something is changing color, and we were able to measure the color density of whatever sits in the reaction vessel, we would be able to get a trace as we measure perhaps the change in wavelength of reflected light, or the way the red light which is reflected from this reaction changes or decreases. Anything like that you can actually measure can help you to determine the rate at which the chemical reaction is taking place.
Exactly. And maybe just to add, on one very familiar chemical reaction, the sodium thiosulfate and hydrochloric acid with the crosses, and you put your beakers across, maybe 3 or 2 crosses, you put them over there, and you've got a solution of sodium thiosulfate. You put your hydrochloric acid, and you measure how fast is the solution becoming milky, cloudy, and until you just can't see that cross underneath. That is another way of measuring how fast it happens. And there, I think mainly they look at the concentration of sodium thiosulfate and see how, just like we did with the bicarbonate of soda here.
That is a term called turbidity.
Wow.
Turbidity. Let me write it down for you so we can all see what it is. It's a very fancy term. Turbidity. Turbidity there.
Yeah.
And that just means becoming cloudy. Okay, so that's the increase in cloudiness. And what Tanyuka is talking about is you put in a Petri dish or something like that, and below it you put it onto a piece of paper with a cross. Now it's sodium thiosulfate. It's sodium thiosulfate. I think it's like that. Yeah. And HCl. Is it?
HCl, yes.
Hydrochloric acid together. And when you react these things together, what happens is that you get sodium chloride, and you get perhaps a gas, but more importantly is you get sulfur, solid sulfur being released. And sulfur doesn't react in water, and so this is going to get cloudier, so a suspension of sulfur in the water. And the cloudier it gets, the less easy it is to see this cross that's drawn on a piece of paper below the Petri dish. And so that turbidity eventually, as the turbidity increases, if you were able to measure it, you would be able to measure the rate at which this reaction was taking place. Good.